in this chapter so far, we've been talking about similar triangles, and we've said that if two triangles are similar, their corresponding sides are proportional and the corresponding angles are congruent. Now, one thing we have yet to speak about is the relationship between the areas of similar triangles. So what I've done here is I've drawn two triangles, and of course we are going to say that these two triangles are similar. So hopefully we can develop the relationship between the areas of two similar triangles by studying this diagram here. So let's add some notation here. Let's say this this triangle here is triangle A, B, C. And let's say the smaller one is triangle J, K, L. Now, because our goal is to talk about the relationship between the areas of the two triangles, I think it's a good idea to draw the altitude, okay? Now, you can choose different vertices, but I'm going to choose from vertex A, okay? It doesn't really matter, but I think based on the way that the diagram is given to us, I'm going to draw the altitude from vertex A. Remember, if it's from vertex A, it's perpendicular to the opposite side. That's what makes it the altitude. Okay, and then we'll do the same thing for the second triangle here. I'm going to draw the altitude from vertex J. So I'm going to add a label here to help myself out. So I'm going to add the D here. Let's say this point is D, and here, this point here is M. Okay, so I've basically broken down both these triangles, the similar triangles, into two smaller triangles. So for example, I've taken triangle ABC and I broke it down to two right triangles, triangle ADC and ADB. So now what we're going to do is we're going to focus on the triangle, the right triangle on the left side. Okay, so let me just hide it. I'm going to focus on that. Okay, triangle ADC and triangle JML. And if you look closely, you know what? I think those two right triangles that I just said, those are similar triangles. But you know what? I think we can prove that. Now, because triangle ABC is similar to triangle JKL, I know that angle C is congruent to angle L. Okay, so angle C, let's write that down. Angle C is congruent to angle L. Now, what else do I know? Angle ADC, hold on, sorry. I know angle C is congruent to angle L because triangle ABC is similar to triangle JKL. Okay, that's the only reason I knew that. Now, what else do I know? Triangle ADC, sorry, angle ADC is congruent to angle JML. Okay, and that's obvious because we said that they were both right triangles, or both right angles there. So that's given. That is given. If we're drawing the altitude from vertex A and the altitude from vertex, so altitude from vertex A and altitude from vertex J, it's given that those two angles are right. So if that's the case, guess what? I can conclude now triangle ADC is similar to triangle JML because of angle similarity. Now, we're going to make not a big jump, but a very important jump here in our logic. So because triangle ADC is similar to triangle JML, we can actually make a pretty nice statement about the heights. Okay, so we know that the corresponding sides are proportional. So let's write that down for triangles ABC and JKL. So that means AC over JL is equal to AB over JK, which is equal to BC over KL. Now hold on a second. this was gathered from the fact that triangle ABC is similar to triangle JKL. But we also know that triangle ADC is similar to triangle JML. So not only is this true, but we can add also a fact that the heights can have that same relationship. Okay, so AD over JM is also equal to the same ratio. That is very powerful because that is going to allow us to determine a relationship between the between the areas of similar triangles. So hopefully you can see that logic. So if I double, let's say if I double JL to get the side length of AC, that means I also double the height of the triangle. Okay, so you know what, let's summarize that. Based on our work with similar triangles above, the scale factor applied to the side lengths is also applied to the height of the triangle. Okay, so if that's the case, take a look. So we also know, of course, the area of the triangle is half times height. So let's say the area of my first triangle is half times base times height. Now, what about the similar triangle? My second triangle? Well, if you apply a scale factor of k, which means that's going to change the base and the height by the same scale factor, because we've proven that earlier. The scale factor, not only does it apply to the side lengths of the similar triangles, but it also applies to the height. So the half stays as half, of course, but b will no longer be b, it'll be k times b, because you're applying the scale factor to that side. And what about the height? You're applying the scale factor to the height as well. So we're going to rearrange this, clean this up. So it'll be k squared half bh. And what do we say half bh? Half bh is the area of my first triangle. That's similar to my second triangle. There we go. All right. So then let's do a very quick example because I think that's going to reinforce our idea here. So let's say I have two triangles. They're similar to each other. Okay, and let's say that this triangle has an area of, I don't know, let's say 9 square centimeters. Okay, and let's say the scale factor is 3. Okay, if I've tripled all the side lengths, what's the new area? So what's the area of my similar triangle here? So the area of the triangle is equal to 3 squared, right? The scale factor squared times 9, which is the area of my other similar triangle. So basically it's 9 times 9, 81 square centimeters. Okay, so yeah, just multiply by the square of the scale factor with the area of the triangle, and you'll know the area of your similar triangle. Okay, so remember, if the triangles must be similar. If they are not similar, then this relationship does not work at all. Okay, so that's the most important part, is really back at the beginning here, when we basically concluded that the scale factor not only affects the 3 sides, but it also affects the height of the triangles. Because once I've proven that triangle ADC is similar to triangle JML, I've concluded what I just said. Okay, the scale factor not only affects the sides, but it also affects the heights of the triangle. Okay, so hopefully now you can see the relationship between the area of similar triangles.